Have you been confused with superposition and entanglement in quantum computing? I could totally understand why you might have that because I've seen a lot of videos who jumps on superposition with spinning coins and everything, and I totally understand you might be finding hard time to understand that. So one of the problem which I see is that a lot of people don't understand how classical computer work on the first place. Then you need to understand how quantum is advantageous or how quantum is working. So once you have this comparison mindset, probably that will help you to understand quantum in better way. So just to brief you on how classical system work, recalling from like history, I remember first Turing machines and everything was the first computer, and those computers were basically we used to transmit one information from one place to another place, and that also reminds me of how Morse code used to work. So Morse code is like think like you want to communicate somebody who is far distance from you with a flashlight or something like this. Like two people have flashlights and they are like your neighbor or something, and you live far away and you can just use flashlights to communicate each other. But to do that you need to have some like pre-planning before that. Let's say you want to have you want to call your friends or something, a neighbor, to a house party something when your parents are gone, something like this. So how you can communicate, you can tell them, hey, if I turn on the flashlight, that means you understand, hey, you have to come to the party or something like that. My parents are gone, something like this. That kind is one of the silly example I have this in my mind right now. So that way you can communicate. And let's say you wanted to also ask him, hey, you wanna wanna bring some booze, or you already have some in your house which is left by your father or something like this. Then you can have another like signal for it, like if I flash it for like two times, after that then you have to bring liquor as well. Or if I just flash it one time, so this way, the rate of transmission of your communication depends on how much flashlights you have, how many times you can blink, right? That way, that is very similar to the clocking if you hear about in microprocessor. Like that is the clocking when we blink the flashlight. So that is the one of way of transmission. And to transport a language or certain text, what we do, we break down a language into the combinations of zeros and one, as you already have understood that. So with flashlight I can continuously stream 010101 like this. Another person can also do, and we can record those blinks and write down on something. That was the Morse code. With light was the problem was that you can only work it in night, and you cannot see days flashlights in day, and you cannot travel distances where there is a barrier or something. So we switched into wire communication, or even like radiation, like wireless as well. But the concept was the same. We will have this 01 text encoded on some kind of frequency and we'll send that. So initial Turing computers were made that, let's say if I encode some data on transmission, like, but that is such a broadcast way that anybody can receive or copy that transmission, and anybody can decode what we are trying to send, right? So they came up with shifting method. So like if 010, I could add plus to it this number or something, like I could flip the 0 into 1 and 1 into 0 something. So these were the encoding method just to hide the basically information. So we developed Turing machines to even decode it. So we will try different keys to those signals and we'll convert it. So we somehow find a method to add or subtract or some kind of combination to those kind of messages and decrypt it. So there, that was the beginning of computing era. It didn't started with making programs and something. This was basically how to decode like transmissions and everything. And when we were working with bits, we understood how we can add things, subtract, and that made the ALU, like arithmetical logical unit for your microprocessor, then control units, and overall, as we developed more into that field, we made a microprocessor or something like this. Like we started with 4-bit and something like this, and that way we could transmit. So what is the role of how quantum communic big picture, right? So the if you think about how the transmission speed is dependent. So the transmission speed is dependent how quickly you can flick this. Like you have to go back to the most how quickly you can flick the torch light, right? The faster you flick, more data you can process. And what is the transmission method you are using? Light, if you're using, then the communication is basically speed of light, right? If you're using wire, then how much time it takes to propagate a signal from one point to another. That is also quite faster. So, and that has to be wired along the time, right? Or then later on we came with this light cables, right? Optical fibers as well. So that also travels with the speed of light. So that is the like how fast we can go. But there is a limitation. Like even the speed of light, I think if you have to communicate from Earth to Sun, I think it takes 8 minutes, right, to travel from the sunlight from Earth to Sun. So you probably need 8 minutes to travel if some information is that far. So what can we do to make these two things faster? So there comes superposition. Superposition is like, instead of think like a white light is a mixture of lot of colors. Think that this mixture, instead of having 7 colors, it is only mixed with 2 colors, red and green. Think like this. A different proportion of red and green would represent a white light. Like if it is a 50-50, then it's white light. I'm just giving you an example, analogy you can think like. So if we could have this different ratios like of red and green, there we could represent a lot of number, right? For us, for a machine, it's only, I can only send two information in single torch, right? 0 and 1 flashlight on and off. But with and for humans as well, for humans in one character we could 10 like 8 like 10 digits. Like if I've given one character value, I could just 10 0 1 2 3. So we have more freedom of information than even machines, right? Same way, we could, instead of 0 1, we could have different color of light which is made from the different ratios of red and green, as I give you my assumption. Different, if I, so it will be, sometime it will be purple, sometime it will be yellow, sometime it will be brown or something. So now I could send so many signals to my neighbor, like, hey, my parents are gone, it will be purple. Bring liquor, it will be dark green. Do not come, it will be red. Some, like, more the ratio I have, the more information I could send just with one blink of my flashlight. So that is superposition, like quantum. So classical bit can only be 0 1. Quantum bit could have more, just like we could have different ratios of light. A quantum bit could be like multiple, like it could be a ratio of 0 and 1. Sometimes it will be 60% 0 and 40% 1. Sometimes it will be 70% 1 and it will 30% 0. So we could have different ratios, just like light we could have. That is like superposition. And what is entanglement? Entanglement is basically we could connect these two torches like a far distance. Like if I do something with one light, I would immediately know what happened to the other flashlight, something like, or the receiver with whatever the light sensitive receiver I have. Or like think like two bits are connected. So what usually happens is how we communicate is like each bit are made from register. So you can think this register made from 3 bit, like three digit I can store 00, 011 or something till 111. So these register could hold a lot of information. And how this information is passed is basically they use buses. Like these yellow lines are like buses, right? And how this bus will work, let's say if I have to transmit some information from register A to B, uh, we will not directly, there will be no wiring from A to B. Instead we will use bus. So whatever the information I have, I'll pass on to this bus, right? And that bus will take the information over here. So I'll pass this information over here, and then it will go to register B from here. Like this is information will go here. And what if now I wanted to transmit B to C, but I cannot do it because the information of A is already on the bus A, this bus A. So if I write B back over here or something, anything I do, it will like get multiplied or it will get diluted or something like this. So what do you can, we can pass the B to the other bus and then use this to pass it over here. So all that transmission of information happens through these lines, electrical lines, and they're not even directly connected. We use this common bus because if I do, because there are so many resistors or something like this, it will become very complicated and we will not know how to control them, right? It will be complex. So many switches and this kind of thing would have to be added in this thing. So this is like what do we say, this reminds me of a very good example of early days, is that before microprocessor we would design a different hardware to operate any electrical device, like a washing machine or a fridge or a calculator or whatever. Like there will be a specific hardware made for each of them. But as soon as we have this general universal microprocessor, we applied microprocessor to each of them and we'll change some software, and the hardware was fixed. and we'll just change software for the specific device, for fridge, for electrical appliances or whatever, like, and washing machine and these kind of thing. So we what we do, we didn't have to create different hardware for different thing. Instead, we could have a common hardware and we can change software, because changing software is easier. No materials are required, there is no hardware problems or something like this. Software is easy to write and everything. So it was a very good idea. But we came to a point where software would not solve. There are problems in the world with software, you cannot solve it. We need to have a different hardware for that problem, right? We need to have an analog computer, quantum computer, GPUs or something, like different hardware to solve a different problem. And most of our systems are made like very strict, like it is very hardcore. We cannot change the hardware, you can only change software. But what quantum computer comes with, it comes with a flexibility that comes with entanglement. What entanglement gives you? Flexibility to join any hardware. Like instead of registers, we would have what do we call it, we would have qubits. Registers are a combination of bits, so I'm just minimizing it to qubits. So qubits will something like this, and each qubit, this H is like a gate, just like a OR gate, AND gate, something like. There are gates on classical computer, same way there are gates on quantum computer. This is a superposition, like this gate has helped you to achieve superposition or something like that. But the point I'm talking is that I can connect any qubit or bit, and you can think of a group of qubits as register to any of them. I could have like on run, I could have, there is a code for it, and you can connect these two any wiring. Like what entanglement does, help you to have a connection without wire. It could, you can annot and you can change anytime. It doesn't have to be matching to this. There could be any kind of connection between one qubit, and that is not flexible with classical number. Their bits cannot have different buses joining to them, and that's the power of quantum computer. And these are entangled qubits. And what entanglement gives you is that it doesn't require wire. These connections are not wired connection, they are just entangled, right? There is a lot of hardware thing, is how you have to go deep into hardware. How these connections are made is basically, so there are multiple ways you can make a quantum computer. One of them is like, think like a hydrogen electron, right? And electron, they will have multiple like orbitals, and if they jump from one orbital to another orbital, one of them orbital could be zero, where there is a least energy, and if the one gains the energy, it becomes one. So the qubits could be this levels, right? These orbitals could act as the 0 and 1 state. Like the lower what do you say, the lower orbital could act as 0, and the higher orbital could act as 1. And when it is as lower, it could be 0, and when it jumps to 1, it becomes. What is superposition? Basically, when the electrons are in these orbitals, they are not like a solid rounded shape or something, like they are like a cloud. So when it is a 1 or like 0, like 0 is basically a big probability of a cloud which will be on the, which will like, it will be like a fluid kind of thing, cloudy structure on the lower level, lower orbital, right? That will represent 0. And when the state is 1, that time that cloud will be more denser on the ring of outer orbital. And if it is 50-50, then it will be cloudy in the middle. And if it is 70-30, whatever the side is more, there will be the more density of the cloud. So that is like this. And when we want to entangle them, hit the we hit two kind of like think like two hydrogen electron in different of their shell. And simultaneously, if I hit it with certain frequency of photon or something, like they both get entangled. Basically, they both get connected. So that is one way of there are other way of making entanglement that I could also speak about if you want. This is one way of making quantum computer, and there I could entangle it. So this entanglement doesn't require hardware, just like single photon hit will entangle two of them, right? There are many ways to do that. This is one of the way. So what is the advantage with quantum computer? That I could have any kind of hardware connection. It's basically you are programming hardware instead of software. I'm writing code to change the hardware in the runtime, right? Whatever the classical system was, that the hardware was fixed, we'll write software, the input or something, and we get the answer. Now this is a different kind of programming where the input remains the same, and we change hardware to get our solution. So that is the benefit we have. And one of more the benefit is that I talked about superposition, right? And how superposition work is like, let's say in classical computer, I have to pass 8 inputs, like 8 kind of different inputs. in classical computer. Let's say if I have to pass eight input, we call something is clock. Like think like this register as three bits, and each bit represent one of the information, right? Eight state. Like the input of some problem is eight inputs, right? One, two, three, four, five, eight, and I want to apply certain operation in one, two, three, four, five, six, and eight. So how we will input this kind of thing to a classical system is basically we'll send the pulse, like we call it clock, right? Just like the blinking of the torch, like how we blink, sometimes it'll be zero, sometimes one, zero, zero, one, something like. The more faster we blink, same way we have this heartbeat kind of clocks which we generate in a wire using electrical pulses, right? Basically giving more potential. When we give more potential, it clicks up, that becomes one, and when it goes back, it becomes zero. So you have to send these three pulses to get me eight values, and I can do a lot more operation like this. So at least the clocking we required is eight times. So eight, if the clocking speed is one clock per second, something like this, then 8 second I required. If it is faster, like some fraction of speed of sound or something like this, still it will be 8 time, whatever the lowest unit it is, right? So 8 time I have to give this clock to get these eight values, and then I can do operation. But with quantum, with the power of superposition, right, we could have three qubits like this, and we could apply Hadamard gate on it. Hadamard gate is just like a gate which help us to, what is basically does it whatever we have, like whatever the, as I told you about orbitals, right? It will put the cloud in the between of two orbitals, right? That is basically giving in superposition. What superposition help it is that if I have three qubits, it randomly has 0 1 0 1. Basically, if I put it in a 50-50 state, where the state of that qubit could be like in the 50-50, like it neither be zero nor like 50-50%, could be zero sometime, one comes sometime, something like this. If I do that, all this will start flipping, and because it is combination of three qubits, all of them are 0 1 0 1 flipping. So every time it is basically going to each permutation. Like with three qubit system, I could have eight possible values, and in classical system, 8 time I have to send these clocks. But in quantum, all of them are flipping 0 1 0 1, basically at like a very fraction, like not even fraction, it is beyond the like time of measurement, within the like limitless small time. At one time I could just pass on eight values, right? Eight values I can directly pass. I don't have to wait for clocks. Even your clock is very fast, there's still that will fight, because at once I could have 0 1 0 1 0 1 1 0 1 0 until 1 1 1. Eight inputs I could directly pass it. So whenever there are problems where you have to pass a lot of input, like a combinational like optimization problem, where you have to pass on different kind of designs or input, and what are the optimal one, right? Whenever you want to, let's say, uh, hacking the password is kind of an optimization problem. Let's say I have a 3 digit lock, and there the password is 1 1 1 or something, so I have to apply it, I have to try all the numbers to break the password, right? With quantum computer I could just go all the numbers in one go. This is one of the reduced down analogy I could tell you. So I don't have to try each clock. So there will be multiple clocks, 0 0 0 1 1 1 0 1 0, and each, like it will take like around, like if it is three digits, so many numbers, something like this. If it is in digit, like I'm talking about digit, like so many numbers, right? Same way with this, I could just immediately have all the numbers input go tried out in that, and it will run fast. So these two properties, there are four other properties, like inference and phase kickback and these kind of stuff, which is more advanced, which I can explain you if you subscribe me and you stay with my channel. I will probably be putting those kind of videos in the future, so that you can understand more complex way of understanding those kind of things. But yeah, this is one of the strength of, there are so many strengths, but this is a simple explanation I can give you if you're coming from the hardware side of computer, or if you're coming from the programming, right? So one of the key advantages is that we could use the power of superposition to input lot more inputs at one go. With entanglement, I don't required wire, right? I needed buses. And what happened with classical system, that buses have this waiting time, like input waiting, output waiting time we call it. That makes a program very slow. But for us, we don't have to wait for information to go on the bus, or waiting input or output time, something like this. And we don't require wire, so I could have many connection to many qubits or bits at the same time. So we don't have to require for anything, and we could just change hardware for our problem instead of writing codes. So that thing is, I think, is the power of quantum computer. I hope this you understand this one. I will be putting more videos on that. Future videos will be more mathematical, so that you can understand the core of quantum computing. I will also talk, if you really interested about talking other ways of making quantum computers, that helps you to get intuition how software works. That I will also be explaining. So I hope you have subscribed. See you in those videos.